to remove the nitrite and arsenic anions. Let's welcome him.
Okay. Good afternoon. I would like to thank Professor Dong for his kind introduction. And actually, from the previous presentation, we have learned a lot about the CDI and BDI. Okay, from Professor Hu. So today I'm going to talk about a title a little different from the CDI and BDI here. Because when we mention the CDI or BDI, we always talk about how to increase the capacity through the material or engineering modification. But in his work, we try to demonstrate how to perform the oxidation and deionization simultaneous, because in the environment chemistry, there's some chemicals is in different states. So I just make two examples here: is nitrate and arsenic. Okay, so I might skip the part of the mechanism of CDI because the professor who has thoroughly introduced the mechanism of the electroabsorption through the CDI and double layer capacitance and pseudo capacitance. We know that. So for the pollutants, actually in environment, some chemicals, some pollutants may in different chemical states. They will lead to different like mobility, volatility, electron activity, and even for the chemicals in reduced form, like the nitrate or arsenic, in this work will be more toxic than the oxidative species. Okay, so we just in this work we just introduced these two examples: the nitrate, the trivalent nitrogen, and arsenic, the trivalent arsenic. So before we do the electroabsorption, actually we have done some electrooxidation of the ammonia before, and we find that some transition metal like the nickel oxide is able to oxidize the ammonia during the phase transformation on positive activity, positive polarity. Sorry. So as you can see, during the ammonia oxidation, the nitrate is the primary intermediate, but for long-term electrolysis, all the nitrate will convert to nitrate. And not just the nickel, also for cobalt or copper, they are able to oxidize ammonia and convert all the intermediates to the nitrate. And for another case is the arsenic. Actually, we know that MnO2 is a suitable oxidant for the trivalent S for oxidation trivalent S to S5. But MnO2 is not a good absorbent. Okay, so in previous we have combined the iron oxide, and then MnO2 as the absorbent to treat the arsenic. And we can see the this bimetal can significantly improve the total capacity. But the point is, in this case, the composite is like the oxidant, okay, rather than the catalyst. So most of the MnO2 is converted to, is dissolved after long-term operation. So just not like the conventional double layer capacitance or pseudo capacitance. In this work, we just see the metal oxide here as the catalyst, right? So when we apply the positive potential, hopefully the transformation of the copper oxide or metal oxide, other metal oxide, will be mediated the electron transfer of the pollutant, and then we have a positive polarity, so we can trap this anion simultaneously. All right, this is the first case how we use the oxidation and absorption to treat the nitrate pollutant. And in this work, I just applied two types of metal oxide, the cobalt and nickel, and just chemical deposition in the pores of the active carbon through the oxidation using hypochlorite acid. So this is quite a simple process. So we use the XRD to verify the formation of the the nickel and cobalt oxidized oxides. All right, this is photometry. And as we know, the cobalt and nickel are supercapacitor. So we know that there is a oxidation, reversible oxidation reduction during the photometry scan. And as you can see, with the presence of the nitrate, there's an additional peak appears around like a 0.8 for both of the cobalt and nickel, which means this material can be a good catalyst to electro oxidation of nitrate. And then according to the peak current versus square root of the scan rate, we know that the oxidation is diffusion control. So when we combine the metal oxide and the carbon, you see, in addition to the double layer capacitance, there is a ability to oxidize the nitrate around 0.8. So we further correlated to the peak current to concentration of nitrate, we can determine the transfer coefficient. You see, compared to the active carbon, is a very low transfer coefficient. And then after the combination, you see all the transfer coefficients greater than 0.8, which means the reactivity can be significantly improved as combine these two materials. So also we calculated diffusion current account for the total capacity. You see, although the composite has very low capacitance, because after combination of these two materials, the porosity will decrease. But you see the diffusion current contribute to total capacity is greatly improved on this bimetal and carbon composite. All right, this is a simple batch experiment to show you that the nitrate removal under constant potential, and of course nitrate will release, but we can calculate the total removal by measure the concentration of nitrate and nitrate in the solution. So the capacity will be influenced by the initial concentration as well as the applied potential. So here we just summarize the performance of this material. As you can see, nitrate removal is not quite different among this material, but when we combine these two, the metal and then active carbon, you see the anion capacity is significantly increased. All right, we just demonstrate some absorption capacity for this material compared to carbon, active carbon. Of course, the metals show relatively low capacity for total nitrogen, but you see when we combine these two material, compared to AC is only 8 milligram per gram, the composite can be increased to 25 is almost 3 times as great as the capacity of the active carbon. All right, this is another case. This is for the treatment of the trivalent arsenic. And this is a little different from the conventional CDI electrode. We didn't use the carbon as the substrate because considering the carbon is normally negative charge. So we found that carbon is not good in anion removal. So in this work, we just applied the iron oxide FeOH as the substrate and incorporate with the MnO2, right, to treat the AS3. And the fabrication is quite simple. We just use the ferrous iron as the iron source and then oxygen as the oxidant. And just condition the pH, we will eventually get the FeOH particles. So we we can just mix the FeOH particle and then magnesium salts in the presence of different oxidants, like the permagnesis, like phosphate, to produce different polymorph of the MnO2, alpha, Armstrong, gamma, and beta. All right, this is and the morphology of the materials. Just as you can see, the FeOH is quite small, it's a nanoparticle scale. And then for MnO2, they just show very different morphology, like the needle-like of the alpha and flaky and the sheet for different polymorphs. But once we incorporate iron oxide into the MnO2, you see they show very similar morphology. It's just like the nanoparticle of the iron oxide intercalate in the sheet of the MnO2. Just like the plaque to inhibit the growth of the MnO2. All right, this photometry, you see the simple FeOH is just like the double capacitor in the except for oxygen evolution at a high potential. But for MnO2 composite, you see there is a reversible peak account for the phase transformation of the MnO2 for all the polymorphs. But when we estimate the capacitance, you see the the FeOH just show very small capacitance, but after the combination, the capacitance is just greatly increased. So let's run the CV in the presence of the nitrate. As you can see, the FeOH is not so active to oxidize the AS3 according to the absence of the oxidation current here. But you can see after we combine the Mn and FeO here, there is an additional peak induced by the AS oxidation, just overlap the current of the phase transformation, the MnO2. So we see that now we just see that the MnO2 here is a catalyst, right? It's just run the oxidation of the AS3 and then trap the total arsenic simultaneously here. All right, we just do some surface chemical analysis to verify the mechanism of the oxidation and absorption. As you can see, after long-term running the AS oxidation and absorption, you see the chemical state of the AS on the surface of the electrode is majorly converted to AS5. So we can propose a mechanism that the iron oxide here is a solvent, okay, it's a solvent, and when we apply a positive potential, the MnO2 will be catalytically oxidized AS3 and trap the AS5 by the absorbent site. And so when we shut down the applied potential, they will release the AS5. Okay, this is some analysis for demonstrating the property of the electrodes. Like we measure the concentration of the total arsenic and then S3, S5. And also we measure the metal ions like the iron and the magnesium. And we know that the dissolution of metal is quite small and even can be negligible. All right. And then pH you show, sorry, this should be the potential. Sorry. This should be the potential. And you can see the capacity can be optimized at around a positive 1.5 volts. And this is effect of pH effect. Sorry. So as you can see, with increasing pH, the capacity drops, and this is expectable because when we increase pH, they will create more surface inactivity, so the capacity will decrease. And of course, we run the performance. You see at least in A-runs electrosorption, the performance, the capacity or the performance of the electrode still remain. All right, we just compare the capacity for these four polymorphs, including the alpha, gamma and beta emission. So as you can see, for a simple iron oxide ratio is only 15 milligram per gram capacity. While when we combine these two material, the Mn and Fe, you see at the optimal metal ratio, just around 20% magnesium, 80% iron oxide, you see the capacity is greatly improved, even 3 times the original iron oxides. Okay, I might make some conclusion here. Just for nitrate oxidation and absorption, the metal hydroxide, the NiOH and COOH can significantly contribute to the diffusion capacity for the composite. And then the nitrate oxidation just at around onset potential, around positive 0.5 volt. All right. So we found that the transport coefficient of the electron can be significantly improved when we combine the nickel and cobalt oxide into the active carbon. So just around 10% combination. Okay, we calculate the more like capacity can be improved from 8 to 25 milligram nitrogen per gram. And as for arsenic oxidation, in this work, we just incorporate iron oxide into MnO2, all right? And the Faraday reaction of Mn3 and Mn4 would be the mediator for S3. So the combination of the Mn and Fe will improve the S5 yield, and we calculate the capacity. Of course, we can increase the capacity for total arsenic compared to original FeOH, is just around 15. They can be further increased up to maybe 3 times, 4 times the capacity of the FeOH after the combination of the Mn and FeO. Thank you. That's all. I think that's all. Thank you for your attention.
Okay, thank you. Time for questions. Short questions. We are a little bit late. Okay. Okay, Chita.
Thank you very much. My